Welcome to Spaceverse, your portal to cosmic adventures. In September 2008, after many years of anticipation, the Large Hadron Collider, the most advanced high-energy particle collider globally, officially became operational. Developed by the European Organization for Nuclear Research, its construction was meticulous and intricate. Over the years, the LHC has profoundly deepened our understanding of the universe. However, a recent occurrence has left physicists utterly perplexed. When the LHC was operated at its highest energy level, scientists at CERN detected an unforeseen and irregular result. Since then, the scientific community has been abuzz with theories attempting to clarify this anomaly. What transpired that was so disastrous? And what are the consequences for us now and for the future of scientific exploration? Stay tuned as we reveal these mysteries and explore secrets beyond imagination. Envision a gigantic machine that stretches across two nations and delves deep into the Earth. Welcome to the realm of the Large Hadron Collider, a stunning accomplishment of human ingenuity created by CERN. This isn't merely a machine, it's the largest and most powerful particle collider in existence, and its history is as captivating as its mission. CERN, the European Organization for Nuclear Research, serves as a beacon of global collaboration and scientific inquiry. Its origins can be traced back to the post-World War II era. As Europe worked to recover from the catastrophic conflict, there was a growing agreement among scientists and policymakers that cooperation was vital for rebuilding the continent's scientific capabilities. In 1950, the distinguished physicist Louis de Broglie proposed the establishment of a shared European laboratory to ignite scientific innovation and promote peaceful collaboration. Shortly thereafter, in 1952, 11 nations united to sign the CERN Convention, thereby establishing the organization. By 1957, CERN was officially operational along the border of Switzerland and France. The main goal of CERN was to investigate atomic nuclei and their components. To accomplish this, particle accelerators were essential. These colossal machines accelerate particles to nearly the speed of light, colliding them to uncover insights into the fundamental building blocks of the universe. Fast forward to the 1980s, and the concept of the Large Hadron Collider began to take form. As scientists' ambitions expanded, so did the demand for a more powerful machine to delve deeper into the mysteries of matter. The LHC was envisioned as the largest and most potent particle accelerator in the world, featuring a 27-kilometer ring of superconducting magnets and detectors. Construction of the LHC commenced in 1998 and was an engineering feat in its own right. Positioned 100 meters underground, this massive loop required collaboration from thousands of scientists and engineers from around the globe. It took a decade to finalize, and in 2008, the LHC was set to embark on its particle colliding journey. But why such depth? In addition to protecting the collider from the surface environment, the depth also cleverly navigated the challenging terrain of the Jura Mountains. This approach eliminated the need for a large vertical access point, resulting in significant cost savings. After all, who would want to purchase expensive land above ground when there was plenty of space below? But what precisely does this enormous underground ring accomplish? In 2010, it recorded its first ever particle collision at a staggering energy level of 3.5 tera-electron volts per beam. To put this into perspective, this was nearly 4 times greater than the previous world record, and it was only the start. After undergoing some upgrades, it now achieves an even more astounding 6.5 tera-electron volts. Visualize 2 beams of particles speeding at nearly the speed of light and then colliding. That's the LHC in action. It has 4 designated points where these high-velocity particles converge and collide. Surrounding these points are 7 detectors, each designed to observe and analyze the various phenomena resulting from these collisions. Most of the time, the LHC collides proton beams, but once a year for an entire month, it shifts its focus to heavy ions like lead. It's like the machine's special annual event. Now you may be asking, why go through all this effort? The answer lies in our unending curiosity about the universe. Physicists are utilizing the LHC to test some of the most perplexing theories in particle physics. They are particularly focused on investigating the elusive Higgs boson and exploring the existence of a broad family of particles proposed by supersymmetric theories. Have you ever heard of hadrons? These are tiny subatomic particles composed of even smaller elements called quarks. Think of them as the fundamental components of protons and neutrons. The LHC is named after these because it collides them to create various byproducts. Many of these byproducts exist only for a brief moment and cannot be studied in any other way. Therefore, every time there's a collision in this massive underground ring, it resembles a mini Big Bang. Scientists gain a glimpse into the very fabric of our universe, its fundamental components, and the forces that bind it all together. Constructed between 1983 and 1988, this underground tunnel measures an impressive 3.8 meters in width and is fortified with concrete. Above ground, there exists a facility packed with essential equipment. Picture a room filled with complex control systems, compressors, ventilation machinery, and cooling units. Now, here's where things get truly astonishing. The LHC generates approximately 15 petabytes of data each year. That's an enormous volume of information to manage. An international partnership led to the creation of a computing grid specifically designed for the LHC. This network is a technological marvel in its own right. The primary goal of the LHC is to uncover the mysteries surrounding a particle known as the Higgs boson. This particle was akin to a phantom. It had been theorized by scientists but had never been observed. Its elusiveness stemmed from its substantial mass. The LHC, with its powerful capabilities, aimed to generate several of these Higgs bosons every minute. It was like setting a trap for a rare creature that many believed existed but had never been caught. But the LHC didn't stop there. In addition to searching for the Higgs boson, it ventured into other unexplored realms of physics. It looked for supersymmetric particles and other hidden marvels of the universe. However, the journey was not without its challenges. Shortly after it began operations in 2008, the LHC encountered a major setback. A magnet failure caused damage to many components of the collider, resulting in a delay of over a year before testing could resume. Nevertheless, once it operated between 2009 and 2013, the LHC achieved groundbreaking discoveries, including the long-sought Higgs boson. After its first successful run, the LHC went into a period of hibernation for upgrades, awakening in 2015, prepared for new explorations. Its second run lasted from 2015 to 2018, followed by a pause until it restarted in April 2022. Now, with an increased beam energy of 6.8 tera-electron-volt, this machine's third run is set to enthrall us until 2026. But something remarkable occurred on July 7th during its third run. Picture Earth's magnetic field as a protective barrier surrounding our planet. On that day, a mysterious fissure manifested in this barrier. This wasn't just a brief anomaly, it remained open for an astonishing 14 hours. Imagine a window unexpectedly left ajar on a stormy night, allowing the cold winds to rush in. This crack permitted a surge of solar winds from the sun, resulting in significant geomagnetic storms. The outcome? Stunning displays of auroras illuminating the sky. If you're a fan of Stranger Things, you might remember Vecna, the monstrous antagonist. Some fans humorously speculated whether Vecna had emerged through this very opening. While that remains a playful notion, the visual spectacle from the auroras was undeniable. So, what caused this crack to form? The culprit is known as a co-rotating interaction region originating from the Sun. CIRs are immense plasma formations created when varying speeds of solar winds collide. Picture two rivers, one slow and one fast, converging into a turbulent waterfall. These CIRs, along with other phenomena such as coronal mass ejections, are propelled from the Sun toward Earth. When they collide, we are treated to a light show, the auroras. In the early hours of July 7th, such a CIR collision led to a persistent geomagnetic storm. The National Oceanic and Atmospheric Administration even noted that this storm was enhanced by a prior coronal mass ejection. Should we be concerned about these CIRs? Interestingly, experts provide a reassuring no. Earth's magnetic field, our protective shield, frequently experiences such cracks. These typically close up quickly. However, recent events indicate they can linger for hours. Imagine living in a house during a storm with a window that occasionally gets stuck open. While most of the storm is deflected, some water might damage the couch. Similarly, while our magnetic shield blocks most space storms, some energy manages to seep in. This can sometimes disrupt our satellites, radios, and power systems. In 2003, Harold Frey compared our magnetic shield to a drafty house's. Most storms are kept out, but occasionally some energy slips through the gaps, just enough to create a spectacle in the sky or interfere with our technology. Fortunately, there were no resulting radio blackouts or power failures. Instead, this cosmic phenomenon offered a breathtaking surprise for residents in Canada and the US, spectacular northern lights. But that's not all. Scientists have revealed a fascinating fact: the sun is becoming more active. In fact, it is exhibiting more activity than they had predicted for this phase in its cycle. What does that imply for us? Quite simply, if you've ever wanted to witness an aurora, your chances have just significantly increased. Over the next 3 years, you can expect the skies to be alive with vibrant colors even more frequently. Speaking of monumental scientific breakthroughs, let's delve into the Large Hadron Collider. You can think of the LHC as a gigantic microscope that enables scientists to examine the smallest particles in our universe. Back in July 2017, it made several astonishing discoveries, including the properties of the Higgs boson. Fast forward to 2021, and the LHC identified 59 new hadrons. In July 2022, it observed a new particle known as the pentaquark, composed of unique combinations of quarks. However, even cutting-edge devices like our beloved LHC encounter challenges. Over time, their efficiency in generating groundbreaking results can diminish, but scientists have a strategy: they upgrade. Currently, the LHC is undergoing an enhancement called the High Luminosity Large Hadron Collider. Launched in June 2018, this initiative will supercharge the LHC, enhancing its ability to detect rare cosmic events. So, what is the LHC's crowning achievement? In its first run, it discovered the Higgs boson. The second run of the LHC provided even deeper insights into this particle. Now, with its third run set to conclude in 2025, scientists at CERN are optimistic about obtaining double the data and potentially doubling their discoveries. The Large Hadron Collider at CERN is preparing for an exciting journey. Imagine this: by 2029, this massive machine, after extensive preparations, will be colliding particles at rates 10 times more intense than ever before. And the excitement doesn't end there. This phase, anticipated to last until 2042, will accumulate data sets that are a staggering 10 times larger than those expected at the end of its third run. If you're curious about why this matters, let's explore the exciting realm of proton collisions. Imagine protons as bags filled with colorful jelly beans. Inside these bags are even smaller particles called quarks, held together by minuscule particles known as gluons. It's like a dance of nature's tiniest components. Picture two bags of jelly beans colliding with each other. Most of the time, the jelly beans, or particles, scatter and regroup into familiar arrangements. However, every so often, something extraordinary occurs. Two quarks or gluons collide directly. This collision compresses all their energy into a nearly infinitesimal point before explosively releasing it. It's in these rare, high-energy events that physicists might glimpse the deeper mysteries of nature. The LHC faces the challenge of protons colliding an astonishing 40 million times per second, generating data equivalent to 20 smartphone photos per collision. This leads to a staggering million gigabytes of data every second. Most events are routine, with only one exceptional Higgs boson event hidden in the data flood. To manage this, scientists use a trigger system to select the most interesting few hundred collisions each second for analysis. Essentially, the LHC acts as a massive microscope to uncover the universe's fundamental building blocks. Its primary goal is to find previously unseen tiny particles that could reveal new cosmic truths. While heavy particles might not be discovered in Run 3, scientists hope to find clues, much like a treasure hunt, leading to greater revelations in future runs. Here's an interesting development: dark matter. You've likely heard of it, this mysterious substance in our universe that is invisible yet constitutes a significant portion of it. Some new particles might be associated with dark matter, but they are so elusive that they rarely reveal themselves directly. It's similar to trying to perceive the wind. While you can't see it, you can observe its effects, like leaves fluttering. At the LHC, we search for other particles that behave strangely, indicating the presence of these unseen ones. However, there's a challenge. Often these signals are so faint that our detectors fail to catch them. It's akin to trying to hear a whisper amid the noise of a rock concert. But with some enhancements in Run 3, we're adjusting our detectors to better capture these subtle indications. And there's more. Plans are in motion for an even larger and more ambitious machine, the future Circular Collider. Imagine it as the LHC's bigger sibling. This colossal particle collider could have a price tag ranging from $9 to $21 billion. Yet not everyone supports this initiative. Some argue that with such a significant investment, we should explore other major scientific projects. For example, consider constructing a giant radio telescope on the far side of the moon, or deploying a device in space to detect gravitational waves, ripples in spacetime caused by cosmic events. Sabine Hassenfelder, a prominent physicist, contends that this new giant machine may not even reveal the mysteries we hope to uncover. It's a bit like spending money on a super telescope that may not unveil any new stars. Nevertheless, with the LHC gearing up for Run 3 and even a potential Run 4, there's plenty on the horizon. It's as if we're in the midst of a cosmic detective story, piecing together clues one at a time, with every phase promising more discoveries. Think of them as episodes in an exciting series, and we're just about to binge watch. One recent surprise was an anomaly in Earth's magnetic field that remained open longer than anticipated. It's akin to finding a hidden door in your home that you never knew existed. What will we uncover next? Max Laughlin suggests that humanity may be in trouble due to experiments at CERN, proposing that high-energy particle collisions have shifted us into an alternate universe, resulting in the Mandela effect. This phenomenon, where many remember events differently from how they actually occurred, is thought by some to be evidence of our transition to another reality, rather than just memory errors. While Laughlin's theory is intriguing, it remains speculative and has faced skepticism from the scientific community. There is no concrete evidence linking CERN's experiments to parallel realities, but concerns about safety persist. CERN prioritizes safety in all its operations. Stringent protocols minimize radiation exposure, with personnel using dosimeters and controlled areas for radiation hazards. Robust engineering designs and shielding are employed, and chemical safety is ensured through careful handling and disposal of hazardous substances. Electrical safety and fire prevention are also critical, with regular inspections and compliance with international standards. CERN provides comprehensive training for emergency preparedness and offers on-site medical services for health issues, while environmental precautions are strictly adhered to. And that's it. Thanks for joining us at Spaceverse. From CERN's groundbreaking experiments to the mysteries of dark matter and dazzling auroras, there's so much to uncover. Stay curious and don't forget to like and subscribe. Keep looking up, and we'll see you next time.